Students, today we will discuss the conservation of mass and energy in closed and open system. First, we will consider a closed system. System which contain basically suppose C components. That means this system is made up of C components. We will write suppose that component with gamma is containing suppose 1, 2, 3, 4 and so on up to C components. And among which suppose a chemical reaction may take place. So in such a system, any variation of mass will result only from the chemical reaction. That means variation of masses will result only from the chemical reaction. So the change of mass, suppose mass is represented by small m and of this gamma, that means the change of mass of suppose component gamma during suppose time interval dt will be simply given by this relation, which is change in mass of the component gamma will be equal to mu gamma. This is simply stoichiometric coefficient. M gamma, this is molar mass of component gamma, and d zeta. Zeta is simply the extent of reaction, or you can say degree of advancement of a reaction also. So here this capital M gamma is basically molar mass of component gamma write here, and this new gamma is basically equal to stoichiometric coefficient. Metric coefficient in the chemical reaction. And one more point you have to remember, that this stoichiometric coefficient by convention, this stoichiometric coefficient is taken as positive for products. I can say for the product, and negative for reactant. And this zeta is simply degree of advancement of the reaction, or you can say extent of reaction. So this zeta was basically introduced by a scientist whose name was introduced by Donda. Okay. Now, to understand this equation first, we will simply take example here. Suppose a reaction is going on, nitrogen plus 3 times hydrogen gives 2 times ammonia. So from equation 1 we can write change in mass upon mu gamma, molecular mass gamma will be simply equal to the change in zeta, you can say. So applying this relation to this reaction, we will simply write, therefore it is very simple, change in mass of, suppose first is, this is the reactant side, it is nitrogen, we will write in subscript nitrogen upon minus, here we have taken the value of mu gamma for reactants as negative, so it will be molecular mass of nitrogen. So this will be simply equal to change in mass of the hydrogen here, and it is coefficient divided by coefficient, but we have to take it as negative value, so we will write minus 3 and molecular mass of hydrogen, and it will be equal to the change in mass of ammonia now, dm ammonia upon coefficient is 2 and V gamma will be equal to plus 2, so it will be simply 2 m ammonia, and this will be simply equal to the zeta. We have simply applied this relation, which was the equation first. Basically we wrote that equation first in this form also, so we have taken a simple example of formation of ammonia here. So for this case also the total mass total mass of the system is given by, that means the m will be simply equal to summation of the masses in different reactions. Suppose a number of reactions are taking place, but they are you can say continuous reactions, and we will simply add their masses. So summing equation 1 over gamma, that means gamma is nothing but number of basically these reactions here taking place. The principle of conservation of mass for a closed system is expressed as, we can simply write it as change in mass, total mass will be equal to summation, that means we have to sum equation over gamma, so we will write it as mu gamma molecular mass of gamma component and multiplied by d zeta, which will be simply equal to 0. So this is our suppose equation number, this was 3. The equation summation gamma mu gamma m gamma will be equal to 0. This is simply called the stoichiometric equation of chemical reaction. So instead of mass, basically instead of the mass of the component, it is convenient to use the number of moles, the mole number simply. That means we will not use the mass, we will use number of moles. So for example n1 comma n2 comma so on up to n gamma. So we can write the equation, therefore the equation 1 as, basically we are dividing mass upon molecular mass, that will be the change in number of moles. Suppose gamma will be equal to simply the coefficient gamma and multiplied by the extent of reaction. So this is equation number suppose 5. So here equation 4 and this equation 5 basically introduce this zeta. So the chemical reaction rate per unit time, That means suppose a chemical reaction is going on and its extent of reaction is d zeta, and if we take the per unit time, that will be the chemical reaction rate per unit time. So it will be defined as, that means it will be simply equal to, this is not nu gamma, but this is the rate per unit time. Nu, it will be equal to d zeta upon dt. So this is equation number 6. So it is basically this nu, it is simply a ratio between, you can say, the increment d zeta and the time interval. So from equations 5 and 6, the increase in the number of moles, that means n gamma, will be given by, you have to simply divide it with the time interval, so it will be equal to mu gamma mu. So this is equation number 7. So this is equation number 6 and this is equation number 7. Also equations 4 to 7 up to this equation, they can be extended to R simultaneous reactions, suppose designated by indices. Indices, suppose rho, for first reaction rho will be equal to 1, second reaction 2, and third 3, and suppose R reactions are taking place, but they are simultaneous. You will understand this simultaneous in a bit, because we will take an example there. So the total energy, or you can say place of energy, we will use the total change of mass, suppose dm gamma will be then equal to sum of changes, resulting from the various reactions. That means we can write, if suppose R reactions are taking place, or you can say the continuous reactions or simultaneous reactions are taking place, so we can write dm gamma will be equal to m gamma summation. Suppose the reaction starts from number 1 and goes up to R mu gamma rho and d zeta rho. So suppose this is equation number 8. Here V gamma rho basically denotes the stoichiometric coefficient of gamma, but suppose in the Roth reaction. So we can write the rate of the Roth reaction as V rho will be equal to d zeta upon dt, but this is of the Roth reaction. So this is equation number 9. So to understand this simultaneous reactions and how to calculate this change in number of moles or change in number of mass, we will take an example here. Suppose considering the following two simultaneous reactions. Suppose in the first reaction, 2 times carbon is basically mixing with oxygen, forming 2 times carbon monoxide. Suppose you can write it as rho is equal to 1. That is the first reaction. Next will be carbon reacting with oxygen to form carbon dioxide. So here reaction, it is reaction number 2. That means now we can write the above formalism here. What we have done, that suppose D change in number of moles of carbon will be equal to minus, here you will see it is carbon number, it is in the reactant side, so it will be minus 2 B, and this is going on in reaction 1, we will write as d zeta 1. In the reaction 2, this is also in the reactant side, so it is also consuming here, so we will write minus d zeta 2, reaction 2. Similarly, for D and O2, we will write here it is in the reactant side, so we will write minus d zeta 1, minus, here also on the reactant side, and its coefficient is 1, so we will write minus d zeta 2. Now for the change in number of carbon monoxide molecules, here it is in the product side, so it will be obviously plus gamma, that means the no will be plus, and coefficient is simply 2, so we will write as plus 2, and this is also in the reaction 1. And similarly we can write Dn carbon dioxide as d zeta 2, that means here this coefficient is 1, so it will be plus 1 d zeta 2. So this way these reactions are applied. Okay, now we will consider an open system. Now consider an open system here. So for this system, the change in mass, we will write it as dm gamma of component gamma is basically split into two terms because this is open system. So we have already done for open systems that we can split these into two parts. So one will be called as DEM gamma and other will be called as DIM gamma. Here DEM gamma is mass exchange with the exterior, or you can say surroundings, exterior surroundings. And this DIM gamma is basically the mass exchange with the internal system, you can say, or you can say mass exchange with the internal system, or you can in other words say internal exchange changes inside the system. So from equation 8, the last equation, we can write it as d gamma will be equal to DEM gamma plus M gamma summation rho is equal to 1 to R. Suppose R simultaneous reactions are taking place, and this is gamma rho and d zeta rho. So suppose this is equation number 11. Or we can write in terms of number of modes as dn gamma will be equal to den gamma plus summation, because we will divide throughout by this molecular mass of gamma component, so it will be equal to 1 summation rho is 1 to R and will be gamma rho d zeta. So this is equation number 12. Now summing equation 10 over gamma, so equation number 10 is, this is basically equation number 10 here. If we sum equation 10 over gamma and taking into consideration that the stoichiometric equation, which is summation gamma mu gamma m gamma will be equal to 0. We'll find that here simply change in mass will be equal to TEM. So this relation basically expresses the principle of conservation of mass, but in open systems. It basically shows that the change in the total mass is equal to the mass exchanger with the exterior or surroundings. Okay, thank you.